And it is exactly classical holonomy group of this flat manifold. And so why we use this name holonomy group here? And how we define holonomy representation. Now, if we have such short exact sequence, we can define the map from this finite group to general linear group over Z in the following way just by conjugation. So we take, there is the EI, there is the basis of this space, and this is, and for any element from H, from this finite group, we take pre-image of this element, and we conjugate this on this element of basis, and this defines the homomorphism from this finite group to this group. And what is important here, we use the maximal abelian groups. Maximal abelian groups is equivalent that this representation is faithful. This is important here. This holonomy representation is faithful. So if we look on this crystallographic groups now on Lieberbach groups, because we shall consider mainly torsion-free case, we can try to classify to such short exact sequence is equivalence, it is from basic algebra course, it is equivalent to some element in the second cohomology group. So any such short exact sequence is defines some element in the second cohomology group, this finite group in G to N. But what is important with coefficients is this holonomy representation. And this coefficient means that the calculation of such objects is not easy. So that is one of the main problems in classical classification. So if we have holonomy representation, we can define, or we can give equivalent definition that any Lieberbach group of dimension n with holonomy group G, which is subgroup of faithful subgroup of GL and Z. So that is element, define some element is equivalent to some element in second cohomology group. That is, and I will formulate immediately some very easy and very nice criterion for torsion freeness. I think that everyone, you don't need to. And this element in second cohomology group defined by short exact sequence to be torsion free if and only if restriction to subgroup of order P, so P minus 1, and here we have such diagram. So to check torsion freeness some crystallographic groups, it means to check that the restriction of this element in second homology group is non-trivial.
Sorry, this different P's, they probably have different meaning, can they?
Yeah, so I will use here H. Sorry. H holonomy. So some homomorphism, it is not some homomorphism, epimorphism from group to this finite group proportion. So that means that if we have any torsion, so that this group here, this element, so if we have torsion element, we can reduce this to order P, so that it belongs to this group, and that means this short exact sequence splits what is equivalent to this, that this element is trivial after restriction. So that is easy element, and we have. So I have already defined what is the flat manifold, and so the easy examples of flat manifold they are following. So there is any product of sphere. So torus is obviously with flat metric, which is example of flat manifolds, and also another easy example is Klein-Bottle. So in fact here we have classification of two-dimensional flat manifolds. There are only two, and there is of course 17 crystallographic groups in dimension 2. And what are the methods of classification? So we know that such object is a finite number such object in any dimension. So we are interested. What?
Very silly question. So we told that what is the method of classification? I ask you, recall me what do you classify right now?
Torsion-free crystallographic group. What is equivalent to flat manifolds classification of flat manifolds? That is. So let's start. So in dimension 2 we have only Klein-Bottle and torus. So let's go to dimension 3. So in dimension 3 we have only 10 flat manifolds. And it was classified in 1936. And there are two papers. One is some W. Nowatzki from ETH, and he gave classification of 10 flat manifolds, and another one, there were both name papers given, Hamsche, Venn. Hamsche and Venn and Hamsche, I always forget, but one of them was killed during the Second War, but second one, after the Second War...
Uwaga, to jest po polsku.
That's okay. It's understandable.
Remark. And this, the second people, and after the Second War, this second guy was a professor of agriculture at Bonn University. And teacher group told me that he knows him, that this guy who classified this. And then we have computer program Karat, which you can find on this on Aachen Rheinische Westfälische Technische Hochschule webpage, where is full classification of flat manifolds in dimension 4, in dimension 5, and in dimension 6, and there are the numbers of such objects. And what is and here I would like to mention also in dimension 4, interesting because Enrico Calabi, which probably for geometrists were now mathematicians, in 1956 gave in Bulletin of American Mathematics, there is a paper with one page only, which gives exactly number of, which classify manifolds in dimension 4, in which way. And that is because this is classical way. So here they use this short exact sequence. So the method, this Karat program, this Karat method is following. So the first step is classification of the subgroup. Finite subgroup is this group. So it is in each dimension it is only finite number of such group. And also there is a finite numbers of G modules over. And the second method is classify the second cohomology group of this module, what is equivalent here to calculate the first homology group Rn. So from long exact sequences to groups are equivalent. The long exact sequence Rn by so, and since over real numbers any cohomology over real numbers is trivial group, so that means that we have this isomorphism. So there is a program for calculation of this group, and then decided which groups are isomorphic. Decided which groups are isomorphic. So there is the methods of Karat, and this gives us this classification up to dimension 6. In higher dimension, there is two. We can only consider the special cases, and we can use this program to decide it in which groups are in small class. But what is one of the reasons is that we have, for example, the subgroup. There exists subgroup of 6-dimensional linear group over Z such that the second cohomology group is very big.
It's conditions with 6 form of Z? Yes?
Yes.
It's correct, yes?
Yes.
6.
Yes. So there is a very large cohomology group, and to decide it without computer it is impossible. And these people and come back to Calabi. Calabi used this following method, that if we have any flat manifold in dimension 4, we can consider, and if the first Betti number is not 0 of such group, then we can construct Calabi fibration, where the fiber is again flat manifold. So in algebraic language, it means that we have pi1 and we have